numerical problems on the effects of quantization and rounding off, and what are the other types of problems that we encounter while quantizing in a digital system. I will start with a simple example first. Consider a transfer function Hz, a simple second order system. So, it is like this. So, determine the modified transfer function after quantization of these parameters 0.5 and 0.45. Okay. Take b equal to 3 bits and take first a direct form and then a cascade form. In a cascaded form, these are the two factors. In the direct form, you have to take the product, get the quadratic form. Okay. So, let us see, first we consider the direct form. What will be Hz like? One minus 0.95 z to the power minus 1 plus 0.45 into 0.5, so 0.225 z to the power minus 2. Agreed? So, let us quantize these two quantities. So, 0.95 10 is 0.111001. Check whether this is all right. So, minus 0.95 will be 1.1111001. Now, if we truncate it, this will be 1.111. Okay, and that gives me its value is minus 875. Agreed? 0.225 similarly will be 0.001110. After truncation, that will be 001. That is equal to 0.125. So, Hz will therefore be approximated as 1 minus 0.875 z to the power minus 1 plus 0.125 z to the power minus 2. So, in the direct form, this function has been modified to this. Okay. Then in the cascade form, it is 1 by 1 minus 0.5 z to the power minus 1 into 1 minus 0.45 z to the power minus 1. So, I can take this as H1, this as H2. Okay. So, I have to approximate these two quantities. 0.5 is okay. If I take minus 0.5, it will be 1.100. So, that will be in 3-bit approximation remaining as it is. So, that is equal to minus 0.5 minus 0.45 will be 1.01110. See where it ends. all right, how it goes. So, approximation is 1.011. So, that gives me minus 375, all right. If I make 3-bit approximation, just truncation, okay. So, this will become Hz becomes 1 by 1 minus 0.5 Z inverse into 1 minus 0.375 Z inverse, okay. Now, if I multiply, what kind of denominator do I get? 1 minus 0.875 Z inverse plus 0.375, half of that, 1875 Z to the minus 2. Now, compare the two with the original one. Original one was 1 minus 0.95 Z inverse plus 0.225 Z to the minus 2. If I approximate this in the direct form, then it is 1 minus 0.875 Z inverse plus 0.125 Z to the minus 2, okay. And in this case, it is 1 minus 0.875 Z inverse plus 0.1875 Z to the minus 2. So, this coefficient is closer to this one as compared to this one. The other one is distorted by the same amount. Now, one thing is clear, if you factorize it, then some of the factors may remain as it is, all right. So, in the cascaded form, we have discussed earlier also, in cascaded form, in each block the particular root will be sensitive to only one coefficient or the coefficient associated with only that block, okay, when you are rounding off a truncate. It will not be affecting the other poles or zeros. So, this is the advantage of cascaded form. You try to restrict the sensitivity of the roots, their dependence on the parameter truncation within that particular block. Next, we will take up the issue of limit cycle oscillation. Limit cycle oscillations are because of the truncation we have seen in case of say in case of parameter truncation or rounding off, there will be some errors, all right. We represent, especially when you are multiplying a quantity by a constant, the end product will be quantized along with an error, all right. Now, if you are having a stable filter, all right, and if you are giving a finite input, after some time, say in an IIR filter, after some time the output will gradually come down to 0. For example, if you test it with an impulse, so impulse will give you a response which will gradually come down to 0 if it is a stable system. But if you are having a truncation, then there will be a kind of a feedback, it is something like a feedback, all right. So, there will be a sustained oscillation. I will give an example, it will be clear. So, for a stable filter, say IIR filter, for an input, for a finite input, say an impulse, for a finite input which is gradually decaying to 0, it may be, or an input or an impulse, the output gradually settles down to 0. Okay. This is for an ideal filter. Now, if you have truncation, let us see what happens. Hz 1 plus Az inverse. Okay. What will be Hn, corresponding Hn is minus A to the power n un. Okay. And we can write the difference equation as xn minus A times y n minus 1. Had it been minus, I would have got plus here. So, if I have minus here, then it will be minus plus minus plus. Okay. So, in a finite precision, arithmetic, oscillations may take place. Let us take some values of A, say let A be 0.5, okay, and let us excite it with a finite, let us take delta n with a finite input 0.875 delta n. That is an impulse input. What will be the response? Let us tabulate the response, all the components, it will be clear. This is n 0, this is xn which is 0.875, then y n minus 1 which is 0, A times y n minus 1, that is also 0. We have started with initial value 0, then quantized value of this quantity A y n minus 1, that is also 0, then y n which is x n plus A times y n minus 1. Let us see what will be the final output. In the first case, it is 0.875. One may write this as 7 by 8. Okay. Next, n is equal to 1. This is 0. All right. It is a delta input. So, next moment it is 0, 2, 3, 4, 5, 6, 7 and so on. So, these are all zeros. Let us compute this one. Y n minus 1 is how much? This quantity. Okay. Then A times this will be half of this, 7 by 16, all right. So, that is 0.4375, and if I quantize it by a 3-bit quantizer, all right, then this will be, I will write the quantized value or rounded off value 0.100. If we round it off, okay, it will be 0.100. So, that will be equal to half. If you round it off, so you can add, if it is on the higher side, as you round off a decimal quantity, so it will be 0.100. It will go to the other side, and then this one is half. okay, 0, half, then half of that is 0.25 or 1 by 4, okay. This will be 0.010, this will be 1 by 4. Next, this will be 1 by 4, this will be 1 by 8, okay. Either you write in a decimal form, does not matter, or fraction form. And what will be this approximated as in a 3-bit quantizer? Okay. So, it is 1 by 8. Now, see the fun, 1 by 16. Okay. If you take a rounding off, it may be 001, then 1 by 8, again 1 by 8, 1 by 16, 001, 1 by 8, and it continues 1 by 8. So, it gives me a steady output of 1 by 8. What will this look like? The same thing continues. So, if you look at the output function n yn, it started off with 7 by 8, this is not to the scale. Next is it was half, next it was 1/4, then 1 by 8, 1 by 8, 1 by 8. It is not decreasing progressively afterwards, it is remaining steady here. Okay. Now, if you have a 4-bit quantizer, you verify for yourself, you will find you will be following a similar kind of a table, but this value will be reduced, all right, and 0.875, then 0, 0, 0, the same columns I am writing, and then last one is 7 by 8. Next it will be 1, 7 by 8, sorry, this one will be 0, this is 7 by 8, okay. It will follow this, then 7 by 16 or 0.4375, okay, 7 by 16, and then that will be 0.100, so half, okay. Then follow the same sequence, this will become 0.0100, 1 by 4, is it all right? Next 0.0010, 1 by 8, next it will be 0.0001, 1 by 16, and after that it will be always 0001, it will be oscillating with a magnitude 1 by 16, all right. So, the oscillation will continue, but with reduced magnitude. So, per bit you get the magnitude of that oscillation halved per additional 1 bit. If we change the sign of A, it will be alternating between plus 1 by 8 and minus 1 by 8. You can see for yourself in the earlier table, you just put minus 1 by minus A into yn minus 1 and then see the effect. It will be oscillation with 1 by 8 and minus 1 by 8. For a speech signal, for example, when we have a silence period, there should not be any output. Suppose the signal is discretized, that is we take a digitized signal and then we filter with a digital filter, and then again we convert it back to a continuous signal by D2A converter, and then in that silence period you are having a steady oscillation. So, it will generate a speech with a noisy period, with a noisy sound, when the otherwise period should have been with a zero signal, that is a silence period will also be containing some noise. Okay. So, it is not desirable. Next we take up deadband. The amplitude of the limit cycle now the amplitude is limited to a particular band. Say this in the last example it was either 1 by 8 or 1 by 16, all right. So, we call it deadband. So, during oscillation the quantized value of say A into y n minus 1 in the previous example, because for a delta input x n does not come into picture after n is equal to 0. So, you are quantizing only this one. When the input has vanished, then also it is oscillating, that means it is only this quantity A into y n minus 1, and this quantized value is y n minus 1 or minus y n minus 1, is it not, when A is greater than 0 or A is less than 0. Okay. So, quantized value of A y n minus 1 minus A y n minus 1 should be less than 2 to the power minus b by 2, all right, or y n minus 1 magnitude minus A times y n minus 1 magnitude should be less than 2 to the power minus b by 2, or y n minus 1 magnitude should be less than equal to 2 to the power minus b by 2 divided by 1 minus magnitude A. So, this is the deadband for a first order IIR filter. Okay. For a first order filter, this is the deadband. So, rounding of the product of multiplication that causes oscillation. Okay. Now, there are other types of oscillations due to overflow. This is because of the rounding off. There can be also overflow. So, when you are having an overflow, you will have to control the magnitude. We will see that later on. When the sum of, so there is an oscillation due to overflow. see 7 by 8 plus 3 by 4 or 6 by 8. This is 0.111 plus 0.110. Okay. So, that gives me 1.1101, 1101, 0.5, 0.2, 4 by 8, 6 by 8, 7 by 8. So, this is 1. Is this all right? .101, that is equal to minus 5 by 8. Okay. So, you can see addition of two quantities is giving me a different answer. It is like this. So, it is an adder. If you keep on adding quantities, all right, the total sum goes up, suddenly it becomes negative, all right. Whenever it exceeds 1, this is 7 plus 6 is 13, 13 by 8. If it is up to 8 by 8, it will go up to this point. The moment it becomes 9 by 8, the overflow takes place, so it becomes negative quantity. So, like that. And in the adder, if you keep on adding again some quantities, it will go on increasing, again it will drop. So, this is the kind of response you get. So, this is a dead band, it will be oscillating between these two quantities. This is the transfer characteristics of an adder. Okay. So, the total output varies between -1 and +1. So, how do we modify this? So, we try to modify the characteristics by changing it to this form. That is, you clip it, it gets saturated at 1. So, two quantities when they are added, 7 by 8 plus 6 by 8 is equal to 13 by 8, we will chop it off, we will store it as 1, otherwise it will be stored as a negative quantity, all right. So, similarly on the negative side, if it is going up to -1, then beyond -1 we will take it as -1. So, when you are chopping it, there is a lot of error, is it not? So, that error again will cause problem. Okay. So, there will be signal distortion. You have seen nonlinearities of this kind, you know, for example, in a regular in an analog signal, if you feed a sinusoid, what will be the corresponding output? It is clipped here, is it not? So, that there is a distortion. So, what is the remedy? We try to reduce the magnitude. So, magnitude you multiply by a scaling factor, so that it oscillates within this limit, all right. The variation takes place only within this. So, whenever you are designing a digital filter, you have to see for a given input at any intermediate stage, the overall output should be restricted within this range. So, we should have a scaling factor, a multiplier, to control the input such that at any intermediate point the output should not exceed +1 or -1. Okay. So, we scale the input so that any intermediate variable should not exceed that is at any summing node, at any intermediate variable at a summing node, should not exceed the limit ±1. That is, there should not be any overflow. So, Xn, for example, if we have a second order filter, A1, again Z inverse, A2, okay. We multiply by a factor S naught. This is a scaling factor S naught. Here we have B1 and B2. This is Yn. This intermediate variable, let us call it as Wn. Okay. So, Hz is, okay, this is a constant S naught into B0 this is B0 plus B1 Z inverse plus B2 Z to the power -2, okay, by 1 plus A1 Z inverse plus A2 Z to the power -2. Any question? I should have put -A1 here, -A2. Is that all right? So, I can write this as S naught into some Nz by dz. Okay. Let us take H dashed z is equal to S naught by dz. Okay. S naught by dz, that is the denominator. So, this will correspond to input xz. If I multiply by h dashed z, what would be the output? What would be the output? If I multiply the input xz by h dashed z, it is that intermediate output wz. So, wz is equal to h dashed z into xz. Is it all right? So, xn is multiplied by S naught, and then only this block will give me the output here. So, this is the intermediate variable. I want to check whether this is within that restricted value. This does not cause any overflow. So, what should be the relationship between S naught and h dashed z? Okay. So, Sz, okay, S naught we have taken this, let me write S naught into xz by dz, okay, S naught by dz into xz. So, Sz, let us call it 1 by dz as Sz, then omega n is S naught by 2 pi minus pi to plus pi S e to the power j theta e to the power S e to the power j 0 e to the power j n theta into x e to the power j 0 d theta. Is this all right? D theta, is it all right? Do you agree? Wn, will it look like this? S naught is a constant, and this S, let me write this as okay, because there are scopes for confusion, all right. One is S naught, the other one is Sz. S naught is a constant. Whenever S is put with an argument, that is basically Sz. So, Sz, Z evaluated at 0, at omega equal to 0. No, it does not give you. It should be e to the j theta, sorry, j theta, sorry, j theta, j n theta, this is also theta, sorry, not 0. So, xz into sz. So, basically S naught by dz is xz, sz, so it is sz into xz. Okay. So, this quantity I have taken the inverse transform to get the time domain response. Okay. So, omega squared n will be S naught squared by 4 pi squared, okay. Check whether this is all right. Integration minus pi to plus pi S e to the power j theta squared d theta, sorry, it should be less than this one. If I square it, it should be less than square of this, because this is always less than 1, less than equal to 1. So, if I square it up, it should be multiplied by minus pi to plus pi S x e to the power j theta square d theta. Do you all agree? I can always take the product of the magnitude squared integrated for the two terms separately, and that is equal to, this is known as Schwartz inequality. Now, what is this? Basically, square sum of all the frequency components, is not. So, you apply Parseval's theorem S naught squared, this 1 by 2 pi will go there. Actually I should not have taken 4 pi square here, I should have put 2 pi inside, okay, and then square individually, that would have been better, okay. Anyway, so what I wanted is summation of this square, integration of square of this is same as summation of the corresponding time domain term squared, again for this also. So product of these two, if you take, it will become sigma x squared n for this one, and for this one it will be 1 by 2 pi integrated over 2 pi s e to the power j theta square d theta. This I have written as it is, this one I have written in this form, okay. So because z is equal to e to the power j theta, dz is e to the power j theta into j into d theta. So d theta will be dz by j times z, okay. So we can write this integration as, I will rewrite it, omega squared n is less than s naught squared summation x square n one by 2 pi j this, if you remember, sz square z to the power minus 1 dz. I have just replaced z by e to the power j theta, so it becomes like this, j into z, so that becomes z inverse, all right. So this becomes, this limit of 2 pi becomes a closed path of this. Now this one is apply that residue theorem. Basically this is sz into sz to the power minus 1. Whenever we take magnitude square, it is this, all right. And what is this? sz into sz minus 1 into z inverse dz is basically residue within that circle, and if sz has a pole inside, then sz minus inverse z inverse will have a pole outside whose residue will be 0. So we will have to take this one. So omega squared n, therefore whatever be this, omega square n should be less than sigma x square n when s naught square into this one is z inverse dz is equal to 1. What does this what does this mean? Omega square n, that means at any instant the value of the signal should be less than the energy content in a signal. If it is restricted, if it is less than, the total energy of the input signal, alright, that can be met by putting this condition, alright, then there won't be any overflow. What does it physically mean? Can you conceive of the situation when you are, say it is like this, you are trying to push something, alright, you are trying to push something, you are applying a force. If I want at the total amount of energy that you have spent, if it is more than the energy of at any point, alright, if you measure it as a variable, maybe pressure or any quantity, displacement, if it is always less than the input energy, then it will not have any overflow. It will not have any overflow. It is something like, if you have something oscillating, sometimes the energy of a variable, that is energy associated with a signal in the intermediate stage, may go up, alright, then there is an overflow, but there won't be any overflow if it is always less than the input energy. Okay. So that condition can be met if this is equal to 1. So S naught squared is equal to 1 by this quantity. Okay. So I call this integration 1 by 2 pi j. There was a 2 pi j missing somewhere here. We have made a small slip 2 pi j. So 1 by 2 pi j. Okay. So this integral I call it I. So S naught square should be less than this, where I is equal to 1 by 2 pi j Z inverse dz. What is Sz? It is 1 by dz, is it not? If you remember, we have taken Sz as 1 by dz, alright. So it is dz into dz inverse, alright. So let us consider a second order system. A first order system. Let us take a first order system Hz is equal to 0.5 plus 0.4 Z inverse divided by 1 minus 0.312 Z inverse. Okay. Now what will be dz? 1 minus 0.312 Z inverse, this one. So what is the integration I? 1 by 2 pi j Z inverse dz divided by capital dz, that is this 1 minus 0.312 Z inverse, okay, 1 minus 0.312 Z, alright. Now this is the residue at this point, Z is equal to 0.312 and Z is equal to 1 by 0.312. For 1 by 0.312 it will be 0. So you take the sum of residues, so it will become 1 by finally 1 minus 0.312 squared you know how to calculate the residue. You have to multiply by this factor and then, all right. Which inverse? No, finally it comes to, you can check, you just calculate the residues, it will be approximately 0.95. So, S naught will be 1 by root I, that is 1 by, sorry, I is not this much, I is so much, this becomes 1.1078. So, 1 by 1.1078, which is 0.95. All right. So, if you have a multiplier S naught equal to 0.95, then there won't be any overflow at any stage or at the output side. Okay. Hz equal to 1 by 1 minus 2r cos theta z inverse plus r square z to the power minus 2, r less than 1.0. Draw the direct form. And determine S naught to avoid overflow. Okay. To avoid overflow. So, dz is 1 by hz. Here there is nothing in the numerator except 1. So, I will be 1 by 2 pi j z inverse dz divided by dz inverse, okay, which is 1 by 2 pi j integration z inverse dz. So, that will become hz inverse, okay, into dz. And what is this? What will be this? hz inverse into z inverse integration okay. This we have done somewhere earlier, no? So, what was Hn? Yesterday I gave you a problem. Hn corresponding to this function, you just check up, r to the power n sin of n plus 1 theta, okay, thank you very much, by sin theta, all right, into un. So, substitute here square of this, okay. So, dz that is I, which is equal to sigma h square n will be equal to r to the power 2n sin of sin squared n plus 1 theta divided by sin squared theta summated over n, okay. This you prove and check whether this result can be obtained. 1 plus r square divided by 1 minus r square into 2r square cos square theta plus r to the power 4, okay. So, S naught will be 1 by root I, okay. where I is this much. Now, if you are given a value of r and theta, you can calculate S naught. Is it all right? So, I would request you to verify all these relations. I have taken for granted certain relationships, all right. You derive them yourself. So, in the next class, we shall be discussing about random signals, that is the properties of simple properties of random signals as applicable to the subject DSP. Okay. Thank you very much.